We have Nils, who will be talking about all the goodies of Apple Watches. So, round of applause.
Yes, hi. I'm very, very excited to be here. And do we have slides? We have slides. Awesome. Okay, so I have a lot of stuff to show you today, so I'll get right into it. And I think of all the conferences in the world, this is probably the one where I'm the safest in saying you have all had a look at Apple's platform security guide, question mark. So you all know that Apple is not just spending a lot of money marketing privacy and security, but they actually put their money where their mouth is. And we've seen a lot of improvements in memory mitigations and code signing enforcement and so on and so forth. And so it's becoming more and more difficult to actually develop exploits on iOS to get data from an iPhone. And I'm sure lots of you have experience with that in the audience. And so nowadays, even if someone hands you their unlocked iPhone, there's still a lot of limits on what you can actually do. For example, if we try to steal their Wi-Fi passwords, we will find that this is actually also protected by strong authentication, and we just run into a wall there if we don't have the device passcode or access to biometrics or anything like that. And so if you do security research, you might then start thinking about, could there be another way in to this walled garden? Could there be some way to bypass all of these fancy defenses and restrictions and still steal data from your iPhone in some way? Let's use Wi-Fi passwords as a running example for this talk. And if we think about that for a while, we can kind of imagine, okay, it would be really nice if there was some sort of device that your iPhone implicitly trusts and that it is willing to share all your data with, and that is always around, always connected, always receives everything that's going on in your iPhone. And of course, that's the Apple Watch. And that could be our way in. And so we could say, oh, wait, I have this slide. I forgot about that one. I think all of you know this. Quick vote in the audience. Who's wearing an Apple Watch right now? Yes, most of you, I think. So you are all familiar with the kinds of data that are being shared there. We have instant messaging notifications. We have everything that's going on in terms of health measurement and health sensors that are on the watch, but also more mundane things like calendar events, emails, device settings, and so on and so forth. A lot of interesting stuff to play with. And so what our idea is now is, what if we say, hey, I'm an Apple Watch, you can trust me, you can send me all of this data. What if we could, for example, buy a $20 fake Apple Watch off of AliExpress and flash some custom firmware on that and have that pretend to be a real device, and then I ship that to whoever I want to exploit and have them paired with their phone, and it will just steal all of their data. That would be kind of cool. Now, if we want to do that, we really have to understand the entirety of the Apple Watch system, how this is all working, how the devices are communicating, to see what we can do there. And so that's what I'm going to present you today. And to do that, we have to start at the beginning. And the beginning looks like this. This is probably familiar to some of you. This is the magic pairing visual code. I see someone trying to scan it. That's not going to work. So once you set up your Apple Watch, you will scan this code, and it magically pairs your device, and there's some sort of trust being established, and from that point onward, your devices are kind of bonded. And as humans, when we look at that code, we can't really see what's going on. It's not like a straight-up QR code or anything, so it's difficult to tell what's going on. Luckily, after spending a week trying to reverse this, I found this public GitHub repo by Inside GUI, which loads the private framework that Apple is using to scan and generate these codes, and just slaps it into a custom UI that allows us to scan codes, see what's in them, and also generate our own codes. And so with that, we can actually learn what is in these codes, and that looks like this. It's just a long string that has several parts to it. A lot of them are related to version compatibility and stuff like that. The more interesting parts are, there's the Bluetooth device name of the Apple Watch, so the thing that we actually want to connect to. And then the crucial bit is the bit in the middle. These two values, the Bluetooth out-of-band random and check value. And those are the only two values that you need to do a Bluetooth secure connections pairing with the Apple Watch and to establish a secure Bluetooth connection, and then we can kind of go from there. And the interesting thing here is also that we can learn that all these particles that you've seen on the slide earlier are just smoke and mirrors. That's just a pre-rendered video that is in the watchOS firmware. And what's actually happening is that we are overlaying a kind of watermark on top of that that encodes this string into the red and green channels and like alternating frames so you can't visually perceive it as a human easily. There's a couple patterns on that if you want to look it up, but it's still rather obscure what's going on specifically. So now we understand this code, but we are still in an interesting situation with the Apple Watch here, because what we have is essentially something like this. We have two devices that have never met before. And the Apple Watch specifically has never been connected to the internet. It doesn't have an internet connection. It has no way to talk to anyone. And so establishing trust here is still a bit of an interesting challenge. And so let's see what's happening. On a very high level, communication between your iPhone and your Apple Watch is using a VPN tunnel, an IPsec tunnel that is being established between these devices, and that then provides authentication and encryption for everything that's going on. That's very nice, because now we don't have to worry about the security of the Wi-Fi or Bluetooth channel anymore. But to establish this tunnel, we need some sort of shared key material. That we get from an Internet Key Exchange Protocol exchange, IKEv2, standard key exchange protocol, but this key exchange in itself has to be authenticated. And so if we are in this initial state, that's still a challenge. And looking at what is going on when you initially connect an Apple Watch to an iPhone, you see that there is actually a whole bunch of IKEv2 handshakes happening. We see 4 different ones there. The last 3 are mapped to different data protection classes. And those are actually also the exchanges that lead to the creation of an actual IPsec tunnel. And what sticks out is this first exchange, which also has this pairing.out-of-band key identifier that already hints at what we've seen previously. And for this handshake, we actually never create a tunnel. So at a first glance, this seems kind of pointless. We do an exchange and nothing happens. But if we zoom into that, we can actually look at the messages that are being sent and received. And what we see is that Apple includes notify payloads here. Notify payloads in IKEv2 are essentially a way for a vendor to include custom payloads, custom information inside of a standard protocol. That's usually used to communicate version information, feature availability, stuff like that. But Apple makes quite extensive use of that feature. And in this context, they are actually using this IKEv2 exchange to communicate public key material, which will then be used to authenticate the following IKEv2 handshakes for these data protection classes. And so how do we authenticate this initial exchange? Chicken and egg problem, right? Well, it turns out we just use a symmetric shared secret, and that is exactly what we've seen in the magic code earlier. That's just these Bluetooth out-of-band values that authenticate the initial exchange. Once we've done that, we have established long-term public-private key material, and we can use that going forward. Okay, so now we have most of the initial setup, and we can actually look at what's going on inside of these tunnels. There's mostly two protocols being spoken in there, both Apple proprietary, and those are Alloy and Shoes. Shoes is the simpler one, actually, and that is what allows your Apple Watch to access the internet using your phone's connection. So even when you're on the go, you don't have Wi-Fi, your watch doesn't have a cellular connection, it can use this VPN tunnel, do a TCP connection to a given port on the iPhone, and on that connection send a shoes request. That request will contain the host that we want to talk to on the internet, and it will also contain the bundle identifier of the app on the watch that is trying to make this connection. And then we also have some flags saying, okay, maybe this is a large download, so we only want to do it if we have Wi-Fi connection and not over cellular. Then what happens is the phone receives this request, checks that against the current network conditions, and in most cases, it will just send a reply back saying, yes, connection accepted, go on. And from that point onwards, any byte that we send as the watch on this TCP connection will just get transparently forwarded to our target host, and any reply by the host is going to be forwarded back by the phone to the watch. And so we can negotiate TLS if we want. We can speak any protocol we want transparently with the iPhone as a proxy. Then the second one is Alloy. Alloy is a bit more complicated, but on a high level, it is just a message passing protocol where, for example, the health daemon on your iPhone can say, okay, I am interested in messages of the topic healthsync.classc. And then when the watch sends such a message, these messages have some metadata, they have message IDs, they have stream identifiers, sequence numbers, and so on. But essentially, the watch just sends a message saying, hey, I'm a healthsync.classc message that is being sent over the VPN tunnel, also using a TCP connection to the phone. On the phone, the identity services daemon receives that, looks at the topic, and says, okay, this is a message for the health daemon, I'm going to deliver that to the health daemon, and that can then respond in whichever way is appropriate. Now, if we look at this diagram, you might notice there's some conspicuous free space. That's because I have been keeping something from you. There's actually one more thing going on there, and that is that we have an additional encryption layer that Apple uses for particularly sensitive information in the context of the watch that usually translates to health data. So anything related to health will be encrypted using this custom A over C crypto thing before it's actually getting transmitted over the air. But that's most of what's going on. And so now we can actually start to finish look at what is happening here. For example, if your watch has a new health sample and says, hey, you burned 10 calories in the last couple minutes, what it will do is it will insert that reading into its own health database and then build a nanosync message. That's also a custom protocol that is essentially just designed to keep two SQLite databases in sync. So it has concepts of changes and applying changes to a database. This we then encode into protobuf, and because this is health-related, we apply this additional encryption layer, A over C encryption, at which point we have these two blobs, EKD and SED blobs, and this is then the payload that we pack into the Alloy message. The Alloy message then gets this health synchronization topic, and we can then send that over our VPN tunnel, which means it will get encrypted using ESP, and then this we can actually send over the Bluetooth connection to send these IP-based protocols over Bluetooth. Apple has yet another proprietary protocol that's called NRLP, and then we can finally send that to the iPhone. The iPhone does all of these steps in reverse, applies the change to the database, and now your health information magically shows up on your iPhone as well. So that's how the process works. On a high level, that's what we've learned. Now we can get into the interesting part of rebuilding all of this and trying to get to a point where we have a proof of concept of a fake Apple Watch that you can pair with your iPhone, and that's going to do some malicious stuff to your phone. We start rather simply with AARS. AARS is Apple Accessory Reconnect Service. That's what actually makes this pop-up appear on your phone. And that's essentially just a Bluetooth Low Energy advertisement that we have to copy from a genuine watch. And then with a few lines of code, we have that re-implemented. And if you bring your phone to our proof of concept, it will pop up this pairing message and ask you to pair an Apple Watch. It gets slightly more complicated as we go along. We have to speak some low-level Bluetooth protocols, Apple proprietary protocols, for example, Magnet. Magnet is being used to negotiate additional Bluetooth channels for other Apple services. It's being spoken on a reserved Bluetooth L2 cap channel identifier that makes it a little bit difficult for us to speak this protocol on off-the-shelf hardware without routing anything or messing around with Bluetooth stacks. We have cool tooling for that, though. You can check that out. We have a Wireshark dissector repo for a lot of these low-level proprietary Apple protocols. But so the setup that actually turned out to work in the end was something like this, where we have a small microcontroller that is Bluetooth capable, and we hook that up to Bumble, which is Google's Bluetooth Low Energy Python-based Bluetooth stack that allows us to play around with a lot of these low-level wireless Bluetooth protocols. And once we have that, sending these messages is actually rather simple. We can really easily send and receive messages on this L2 cap channel ID, and with some protocol reimplementation, we can actually get the fake watch to speak with an iPhone and negotiate these magnet channels. And then we get the iPhone to a state where it's like, okay, yes, I would like to do an iKey EV2 key exchange now. Let's exchange keys, let's get this started. The nice thing about iKey EV2 is that it's an open standard protocol, so there is tons of implementations around. The not so nice thing about Apple is that they like to do things their own way. And so they are using very niche cipher modes for iKey EV2 here, and they are using these custom notify payloads that I've showed you before that are non-standard. And so what I just ended up doing is writing my own barely working cursed iKey EV2 implementation that barely works, but it barely works in exactly the way that an iPhone expects it to. So it does all the right things. And that gets us to a point where we can actually do these key exchanges. We can talk to the iPhone, and it's talking back to us, and things are going well. And at some point, we have an established IPsec tunnel, and then the iPhone starts sending data on this tunnel, and then we notice, oh, we haven't gotten to the decryption of that yet. So what we need to do is we actually need to decrypt the ESP data that the iPhone is now sending us. Now, again, this is an open standard protocol. We know what it looks like. Again, in theory, this is as easy as executing these 4 commands on your Linux shell. But again, Apple likes to do things their own way. In particular, they are using implicit initialization vectors, which is a very cool feature if you want to save a couple bytes of bandwidth, but it's not implemented anywhere that I could find. And so we are once again stuck re-implementing this in user space, adding more cursed code. But it's fine, I'm used to it at this point. And with enough magic crypto code, we can actually decrypt what the iPhone is sending us. Now, I'm glossing over a lot of details here. The protocol stack in its entirety is a thing to behold. It feels like a secret language kind of that Apple has developed. There's a lot of custom stuff, proprietary stuff that we have to understand, re-implement, very niche standards being used. But eventually, if we play this game for long enough, we get to the momentous occasion where we can talk Alloy with our iPhone. And this is really where all of the communication between an Apple Watch and an iPhone happens, so this is where the cool stuff is. And now we are in the initial setup of this device. So most of the communication here is the iPhone sending data to us and sending configurations and saying, hey, store this file, apply this config, here's some data. And for the most part, it is enough for us to just say, yes, yes, acknowledge, okay, got it, continue. Unfortunately, that does not work for all of it. For some stuff, we have to look at what the real Apple Watch is sending. We have to craft our own payloads and replies in just the way that the iPhone expects it to, so we can go along with the pairing flow. But if we do that and get it to work for about 350 messages that are sent back and forth, we get to a point where the iPhone sends us your Wi-Fi password in plain text, which is very cool, because previously we have seen that if I have an unlocked iPhone in my hand and I try to see the Wi-Fi password, it asks me to enter the code or do Face ID or whatever, but it doesn't do that to let you pair an Apple Watch. Might be a bit of a long way to get there, but you can get Wi-Fi passwords without entering the device code. And we can look at that in a video here. What we have here is an Android emulator running our fake Apple Watch. Now we are scanning a fake magic code that we prepared that gets recognized by the real phone. You see some iKey EV2 exchanges going on here. We are establishing alloy channels. We are doing all of the setup in the background. Then it takes a bit for the iPhone to actually realize what we're doing and catch up. But that is actually the same for if you pair a real Apple Watch. I'm not sure what causes these delays there. But eventually, we get to a state where everything is sufficiently set up, and the iPhone will let us continue. There we go, with the setup process. And at this point, this is just like setting up a regular Apple Watch. We click continue, continue, okay, okay, and so on. And what's kind of fun is that for the text size setup, we can actually send our own image here, which I thought was really fun to play around with. And we go on clicking next, 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 skip, okay. And finally, we get to a state where the iPhone is content and it's now syncing data, and we are essentially paired at this point. And so now we can see what kind of data the iPhone has sent to us in this process without us really asking, mind you. This is just stuff that the iPhone passively pushed to us. And what we have there, it's a bit small, but I have it bigger on the next slide, is we have the local IP address, we have the iPhone's email, we have our time zone, and we have plain text Wi-Fi passwords of saved Wi-Fi networks that the phone is connected to or that it has stored. Thank you. And so that's fun. What's also fun is that it turns out you don't even have to complete all of this onboarding process. In fact, in the moment that you scan this magic code, our fake Apple Watch is already able to connect to the internet using shoes. And so the moment you scan this code, I can send arbitrary network traffic that looks like it's coming from your iPhone, because it is coming from your iPhone. And that will respect the VPN settings of your iPhone. It will get all the same security exceptions that you maybe have in your corporate network for your trusted iPhone. And maybe you could even do fun stuff like downloading questionable material, using the network connection proxy through the iPhone to incriminate a user, something like that. There's lots of potential there. Some more fun things. It turns out we can actually send our own terms of service as part of the setup. And so for my POC, because I'm a very ethical person, I included this statement in the terms of use, which says, we will be stealing all your data, including but not limited to Apple ID credentials, Wi-Fi credentials, unique device identifiers, and health data. And if you want to read more, you can check out my privacy policy. More seriously, though, if at this point we would have a cool exploit that exploits like the HTML or CSS parsers or renderers, JavaScript is disabled here, unfortunately. But if we would have something like that, that could be a way to get local code execution on the iPhone. Similarly, I already mentioned we can send our own images that are being displayed here. If we have a bug in an image parsing library, we could exploit that here. And then in that way, maybe bypass things like Blastdoor that would apply if we get that same image sent over iMessage or anything, because this is assumed to be in a trusted context. And then, of course, we have all the data that the iPhone sends to us in the pairing process. That also includes stuff like your network, country, keyboard languages. If you are signed into an Apple account, there will be email addresses in there, phone numbers, user identifiers, things like that. But then, also, if we complete this onboarding process, we are now in the role of a paired Apple Watch. And that means that the iPhone pretty much lets us do whatever a genuine Apple Watch could do. And one thing a genuine Apple Watch can do is it can open your iPhone's camera and remotely take pictures. And that even works when your iPhone is locked. So what we could try now is to re-implement the protocols behind that feature and see if we can, once paired, while you're sleeping or in the shower or whatever, open your iPhone's camera, take pictures, have these pictures transferred back to us. And it turns out that yes, absolutely that works. And this is a picture I took that way. So this is me pairing my fake malicious Apple Watch. And then the Apple Watch can open the camera, snap the picture, thumbnail of the picture is getting transferred back over Bluetooth. And that's exactly what you see right there. So that's very fun. There's a lot more potential there, I think. And we are mostly limited by looking at specific features and re-implementing them, and that's just a reversing effort, but there's lots more you could do with this kind of access. One more small thing that I brought for you is a little security vulnerability that has nothing to do with what we've seen so far, but that is related to Apple's IKEv2 handling. We've already seen these notify payloads, and there's a whole bunch of custom ones that Apple uses, two of which sound kind of interesting, namely these update Wi-Fi IP address ones. And it turns out that that's the Wi-Fi discovery mechanism of the Apple Watch. So the first time they connect over Bluetooth, they will include this message that then tells the iPhone, hey, my local IP address is this. If we end up getting disconnected over Bluetooth, you can reach me there. Now, if you read the IKEv2 spec, you will notice that it very clearly says that a notify payload can occur in any context. And IKEv2, being a key exchange protocol, necessarily starts in a state where we have no key material, and so the first messages we send are always unencrypted. Apple only uses these payloads after encryption has been established, but we can now think about, okay, what would happen if we send such a payload in an unencrypted message? And so we can do something like this. We can take an established IKEv2 connection and just inject an unencrypted packet that contains a forged Wi-Fi IP address update. And it turns out that the Apple Watch will actually happily accept that and treat it just like any other payload it receives and apply this Wi-Fi IP address update. And then if we go on to block any further Bluetooth communication, we can actually make the watch reach out to us, to our attacker-controlled device over Wi-Fi, which is cool and should probably not be possible, but it's also not a huge issue because we would still have to complete IKEv2 handshakes, crypto keys, etc. But I thought it was still a fun thing to bring for you today. Of course, we did disclose all of that. Most of it is fixed or in the process being fixed. But I also want to offer a bit of a different perspective. Because so far, we have been treating this as a security vulnerability. I propose a different view which is that this is a cool opportunity. This is an opportunity for interoperability, for example, because it turns out that the Apple Watch interface that people have long been complaining about, that it's not available to third-party watches, well, technically it was available to third-party watches. No one was stopping Pebble from just pretending to be an Apple Watch and using all of the same features. So I think that is a fun area to explore, and we actually did a little something in that area with an app we call WatchWitch. That's an Android app that allows you to connect your Android phone to an Apple Watch in the same way that an iPhone would. And then we have this nice little Android app that allows you to receive all of the health data that your watch collects, and now you can use that in a nice offline-only, open-source, privacy-preserving, locally encrypted way, with some caveats that I am not going to get into. All right, but I said this is a cool thing for interoperability. I think it's also cool for research, because we've seen this alloy protocol. There's about 230 different topics that are being used across 150 binaries in iOS. And so if we are in a position of being able to pretend to be an Apple Watch, we can use all of these services to do cool and interesting things on an iPhone that we might not otherwise be able to do. If we have an iPhone without a publicly available jailbreak, well, we can't execute our own code, but maybe we can use some of these services to push data, get data, activate some features that we might otherwise not have access to. So maybe not everything is bad and horrible and a security vulnerability. Maybe we can have a bit of a more positive mindset here and see this as a nice interoperability win and a cool little thing to enable further research and to be able to poke around in iOS internals. If you want more details about these protocols that I've been talking about all of this stuff, I have a paper out that has like protocol descriptions for a lot of these things, byte field structures. We also have source code on GitHub that does not yet include this cool impersonation demo because that's still in disclosure, but eventually that's also going to be there. So yeah, that might be something for you to look into. And then before I get to the very end of my talk, I have one more thing for you. And that's something that I have been building over the years at this point that I've spent staring at Apple Watch logs. And I've built a lot of parsing code for all of these protocols, for all of these formats to get that to work. And at one point I thought, okay, it would be really nice to just have a nice web UI tool where I can throw stuff into and I can see what's in there. And so I built that, and that's called ByteWitch. And ByteWitch does instant in-browser decoding of a lot of things. It does BP lists in several variants. It does protobuf, it does ASN1, it does NS archives, it does OPAC, it does elliptic curve crypto. There's a lot of stuff going on there, and it has become super useful to me in my research, and I figured it might be useful to you also to be able to paste a payload in there and just get a nice visual representation of what's going on in that payload. I have also had a student invest quite some time in building cool things there. We are now able to compare different payloads side by side. We also do some cool sequence alignment, so you can see this byte in this message corresponds to this byte in the other message. And we also have some cool statistics to determine if something is encrypted or random or just compressed or if there's some structure in there. So do check that out. I would also love to hear feedback from all of you on if that's useful to you, or if it's not, or I also welcome additional implementations of more weird protocols that you know about, weird serialization formats, anything like that. Do give that a look. And with that, we have a couple minutes left for questions, and thank you so much for listening. Yes. Thank you. To my knowledge, you can already just do that in Apple's UI. You can already pair multiple Apple Watches to one phone. It's a bit hidden in the UI, but I think it works. Yes? Mm-hmm. Yes, that's cool. That are the slides that I threw out this morning because I couldn't fit it in the time. The key exchange there actually happens over Alloy early in the pairing, kind of out of band. But it turns out there's a fun little crypto vulnerability in there because it turns out it's quite complicated. It's based on iMessage cryptography, but it turns out they only use that for key encapsulation and not to encrypt all of the payload. And then the payload is just AES CBC encrypted with no authentication, which you really shouldn't do. And then you can play some tricks there. I think you can also read about that in the paper that I've shown on the slides, if that's interesting to you. Yes, back there. From what kind of applications? Sandbox applications. That's a good question. Would you be able to extract data using Alloy from sandbox applications? I think that depends on the sort of interaction that your target app is having with the Apple Watch. If this is a third-party watch that does communicate with the watch, you might be able to do something there. If it's a third-party app that's just local on your iPhone, that would probably not be exposed over Alloy without doing some sort of advanced exploitation and gaining local code execution or something. Yes, in orange. Yes. So this is about disclosure to Apple and what is changing and has changed. I have so far only heard rumors about how the Apple Watch pairing works on iOS 26, but from what I've heard, it seems that they are actually including a certificate now that does some attestation that you are actually an Apple device that's talking to the iPhone, but that's something that I've not yet been able to look at myself. Yes? My approach for reversing the private protocols. It's a mix of staring at traffic captures and trying to find patterns there, and then also statically reversing the binaries in both the Apple Watch firmware and the iOS firmware, and that gives you a pretty good idea of what the protocol should look like. And then once you have a rough idea, you can also start re-implementing that and then use your own re-implementation to send new messages to the iPhone. And then you can see how it reacts and how the details of the protocols work, like how acknowledgements work semantically exactly. That has been also really useful. Cool. Okay, one more. Is the visual pairing the only entry point for pairing an Apple Watch? There's a fallback. You can also just enter a 6-digit Bluetooth code like you would for probably not headphones, but other Bluetooth accessories. That does also work. Okay, cool. Thank you again.